about a lot or think about a lot, most of us who are producers of waste, when we take it out from our house, we kind of unthink it and it's not our problem anymore. And it is one of the fields where we are facing humongous challenges, as I'm sure most of you are aware. We are polluting not only our own planet, but even our pollution has extended beyond our planet. And it is time that we start thinking about new, more creative and circular ways of how we address the waste we produce as a civilization. When we think about the circular principles, many of them are quite hard to implement in waste management strategies. One of the bigger hurdles we are facing in Slovenia is regulation, in a sense that we do not have clear end of waste criteria for most types of waste. If I give you a very plastic example, if someone throws away a perfectly new, untouched pair of shoes, once they are weighted and they're given a classification number as a waste, currently, we don't have legislation that would enable us to put this back into circulation, to give it to someone or to sell it to someone. Slovenia is working on this, so we're hoping that this end of waste criteria to kind of enable or speed up this reuse upcycling process will soon be implemented, so we can actually reduce the amount of waste already at this stage. So today I will be talking about two examples. The first one will have to do with biologically degradable waste that will touch on compost and biochar. And then in the second part, after the break, I will talk a little bit about plastic crude oil, what we can actually do with plastic that we feel would be a much more circular approach to things as opposed to where we are currently. So if I touch on the first part, so in Slovenia, there are still a lot of rural areas where composting is kind of a normal and a natural part of households. A lot of Slovenians have gardens and grow at least some of their own food. So many of them are aware that we can take ways that we produce either around the house or in the household and turn it with time and some manual work back into compost. And in cities, this is, of course, a little bit different. Biologically degradable waste is collected in bins and then transported to waste management facilities where different companies have different ways of what they do with this waste. But the idea is that the food that is left over, or like grass or green cuttings we have from our environment, can be turned back into something that is that can be used as a fertilizer that is returned back to the soil. And this is how we kind of create a circular loop of these essential nutrients in the soil. So I'm partly employed in Center Waste Management in Puconci. This is in the Pomurje region of Slovenia. And for all of this region, there is one single center for waste management. It's called CEROP. And the role of this center is to manage waste from the entire Pomurje region. So dealing with biologically degradable waste, with plastic, with packaging materials, with any kind of waste. We only deal with non-hazardous waste. So mostly we get biologically degradable waste from cities and also from companies that deal with landscape architecture, so grass cutting or tree cutting and similar. And the idea is, of course, to turn this biologically degradable waste back into compost. So Annually, we receive around 8,000 tons of this biologically degradable waste. Cerop has a very well-standing composting facilities. The composting is mostly done indoors, where we monitor the temperature, where we monitor the humidity, and where we can see how the process of composting is actually taking place. We employ thermophilic composting, which means that during the composting process, the temperature is raised. This is done mostly due to presence of oxygen and specific bacteria. The important part of this thermophilic process, so having a higher temperature, is that we kill off potentially pathogenic bacteria, and that this process is also quite sped up when we have higher temperatures. These temperatures are continuously monitored. We also have, Slovenia has pretty strong regulations around composting, and we have to ensure that we have high temperature for a certain amount of time, so that we know that the composting process actually went the way it has to kind of go in order to get a compost that is stable and appropriate to be used as a fertilizer. The most important part of the composting process is actually done by microbes. The composition of microbes is different when we're looking at this first mesophilic phase. Certain bacteria are active here. A different, let's say, composition of bacteria is needed for this thermophilic phase, and of course also for this curing phase. So also different parts of this biologically degradable material are degraded at these different stages. If you can imagine that we get food leftovers, that we get branches, it has to be degraded at different steps during this process, and these bacteria have very specific enzymes that degrade, for example, lignin or cellulose or pectin or hemicellulose, so that at the end of this process will take approximately 10 to 12 weeks. And at the end, we get compost, where we kind of sieve out of the structural material from the finished compost, and we send this compost twice annually for analytics. It goes to an outside lab and is tested on a variety of parameters. And we have regulations where, based on this analytics, compost is kind of sectioned into compost of first quality, second quality, or third quality. And if we reach criteria for first quality, this is one of the examples where products actually have an end of waste criteria met. So once you have first quality and you write proper declaration on this compost, this becomes a product and can be sold and can be used as a soil fertilizer. So for several years now, we mostly produce compost of this first class as a product, and we package it either in bags, or people can also come and collect it in larger quantities. And for compost, we have to be aware that this is not just a typical kind of fertilizer like you buy mineral fertilizers in stores. Because the process is strongly dependent on bacteria, the end product is also very rich in microbial life. So once we put this into the soil, we bring not only nutrients and organic matter, we also bring a lot of varieties of beneficial bacteria, also certain types of fungi that form then symbiotic relationships with the roots. Compost is also a nutrient source that is kind of gradually released. Let's say over approximately 5 years, we saw that compost releases nitrogen and also other nutrients. So it becomes a fairly like a stable or gradient nutrient, so you don't have to fertilize every year. So this is packaged in bags or can be collected via other methods. And this is a first case of where we are kind of incorporating these circular principles. So biological waste that is collected in Pomoria region comes to center Cerop, where it is then composted, produced into a product, and then returned back to owners of gardens and also farmers, mostly in Pomoria region, where it is returned to soil and again creates good environments to produce more food. So this is kind of a nice circular practice where we start with waste in Pomoria and end with the product back in Pomoria region that kind of enriches the soil and enables production of high quality food. Pomoria region has traditionally been known as the kind of agricultural part of Slovenia. So there is still a lot of food production here in very small scale, but also in large scale. And also farmers are very interested in compost, especially the ones who are transitioning to ecological farming or kind of more sustainable farming practices. So we sell all compost that is annually produced, and I would say between 90 to 95% of compost is reused in our region. So this is how we kind of enter into this carbon cycle. So of course, most of the biological waste is made of carbon, and we kind of transform it via the composting process back into a product that is then returned into the soil. So we were quite happy already with this, that this is fairly well functioning. We are one of the rare centers in Slovenia where actually we continuously produced compost of the first class that has that becomes a product and where this cycling is actually possible. But we wanted to take things a bit further. So we know that soil functions as a very important natural sink of carbon, and plants do this already naturally via photosynthesis. They incorporate carbon into their biomass and also into the soil. But with these modern agricultural practices, we see that the amount of humus is actually reduced mostly annually. And these several decades of intense agricultural practices that we have seen have shown that soils, which are actually natural carbon sinks, become actually carbon emitters because humus is reduced. So humus is also made of carbon, so carbon is actually released into the atmosphere. And this is a part where we wanted to do something more. So we started thinking, so how can we either help plants absorb more CO2, or how can we do something that the carbon would be locked into these uppermost fertile layers of the soil? And I did a lot of research, and I did a lot of, I was looking at globally at what can be done, how can we do this? And I was thinking, if this is a natural process, it has to already exist somewhere in nature, where nature is already intensely storing carbon in the soil. And I came across something that is called terra preta. This is called like a miracle soil. This is in the Amazonian forest. There is a very strong legend that inspired many movies and many Hollywood productions. There is a legend of El Dorado, where it was said that a lot of gold is hidden in the soil. And there were a lot of gold seekers running around here and looking for gold, until one archaeologist realized that there are very specific kind of circular or kind of geometrical shapes in these Amazonian forests, in this region where this El Dorado legend was existing. And they dug out this soil and realized that this soil, instead of having like maybe 5 to 10 centimeters of this fertile black soil, it has 2 meters or even more. And this is where it kind of clicked. Aha, this is the gold that was hidden in the soil. And this is soil that is like eternally fertile. This is why it was kind of nicknamed the miracle soil, because it enabled twice, maybe 3 times per year to have crops. And this soil kind of never became depleted. Every year it became more fertile, and this rich dark soil was every year thicker, not smaller like we see mostly in these intense farming practices. So Terra Preta, the secret of Terra Preta, I mean, when you look at it, is this, that this topsoil is just very thick. It can be up to 2 meters thick. And they now know that this was one of the keys of why in such a small geographical area in history, huge civilizations could survive, because they could grow so much food in small areas. And when this was discovered, naturally samples were taken and of this miracle soil and sent all over the globe to different laboratories. And still today, actually, like perfect Terra Preta has not been reproduced. We have learned a lot from this finding, but as I said, all the secrets have kind of not yet been revealed. No one has been able to fully recreate this miracle soil. What we did learn, and what inspired our next step in circular thinking, was that one of the key components of this Terra Preta was biochar. Biochar is actually a biological material that was put through carbonization, and all the carbon remained like solidly bound into this biochar, and all the rest of the materials, minerals, etc., are evaporated via syngas, or just are gasified. And this biochar, actually, if we look at it chemically, is 95 or more % carbon. And when we look at such biochar under a microscope, it has very unique structure. It has a lot of very tiny pores. And these pores are very vital for its role that it can have in the soil. Biochar has been given a nickname that in the soil it functions similarly as coral reefs function in the oceans. So if we imagine coral reef, there's a lot of life where different species find their different niches where they can exist. Well, very similar happens also in biochar, but it's not so much life that we can see with the bare eyes, but mostly microbes, beneficial microbes, find their niches in these pores, also water and nutrients. And when we did experiments with biochar, also like rainworms and things that we can see with the naked eye in fertile soils, we saw that all of that migrated to fields where we had biochar. So it really does function as a coral reef. But also one of the important functions of the biochar is that, as I mentioned, in these tiny pores, tiny droplets of water can be caught. And then when, for example, we have high temperatures and droughts, this water can be slowly released. So it kind of functions as a buffer for water and nutrients, not only as a coral reef for microbial life. and it has a huge surface. So in 1 gram of biochar, there's about 500 square meters of surface. So it has quite unique properties. And when we put such biochar into the soil, there are several things that it does really well. But we learned very fast in first experiments that if we take biochar as such and put it into the soil, we saw that the plants weren't really very happy, that they kind of, that their growth was stunted and they just kind of stood still. So we learned very fast that if we want this to function as a improver of the soil, we first have to load these micropores with something that the plants need. And this was also a lot of this, what we decided to add into this biochar was inspired by this Terra Preta. One of the key findings of this Terra Preta was, besides that there is char in it, is also that it was very organically dense, that there was a lot of minerals and microelements, and that there were very specific beneficial microbes there in this Terra Preta. So in order to ensure that these tiny micropores have everything that the plants need, we mixed the biochar with compost. So we add organic matter and some microbes. We add minerals, usually in the form of like rock dust or zeolite. We are trying to get as diverse minerals as possible, and preferably naturally from local minerals. You know, we have very diverse, let's say, mineral composition of different. Also within Slovenia, we have very different mineral composition of the soil and different layers in the soil, and naturally microbes. And once we kind of activated this biochar with all of these ingredients, pretty miraculous things started to happen in our experiments. So the crucial, so okay, we produce compost, mineral, and zeolite is fairly easy to get, is also used otherwise in agriculture, and also beneficial microbes are not so hard to come by. We can either grow them, or we can also buy them already prepared for agriculture. But how do we get biochar? So usually biochar is produced via a process called pyrolysis. This is a fairly high technology process where biological material is heated up without the presence of oxygen. And what we get out of this is usually gas that is then, it's pretty high energy gas, so we can use it back in the process for heating. Usually this pyrolysis takes place around 600 to 750 degrees Celsius. So we need energy to keep this at high temperatures. And the key product is biochar. So everything that is not carbon gets emitted into the gas, and carbon is stored as a solid carbon in the form of biochar. When we were talking to our ministry of how we could incorporate production of biochar into our processes, they weren't terribly happy with it. So we started to look at different alternatives, how we can, where we can get biochar. And Slovenia is quite, Slovenia has a very long-standing tradition of making charcoal. It's a very, very long tradition already, since many hundreds of years ago. People in Slovenia were making in these kinds of heaps charcoal. But this process takes place at around 300 degrees Celsius, which produces charcoal that has much less surface. So we weren't terribly happy with this solution. So what we did is that we connected to many of the plants for electricity production that use clean biomass as fuel and use pyrolysis as the driving process to produce electricity. And they had biochar as kind of a side waste, with which they practically didn't know what to do. We collected many of these samples and sent them all to analysis, and we found a few that were really very high quality. In this production of biochar, it is very important that the temperatures of the process are very stable, because once they start to kind of go up and down, we can get a lot of chemicals caught in this biochar, and that is naturally not what we want. In most cases, the most common pollutant is polycyclic carbon hydrates, which are pollutants, and we naturally don't want them neither in biochar nor later in the soil. So we found 2 electricity producers that do have a very constant temperature, and actually have a mechanism that when this temperature goes up and down, the process is shut down. So if biochar is like a side product, it is of very high quality, and we went into a cooperation with them. They were actually very happy that we are taking this biochar from them, because their sole interest was production of electricity, and this biochar, this kind of black thing that comes out, was for them hassle. It was something that they wanted to get rid of, and so we found the perfect cooperation. And we did the activation as I described before, and we started experiments. And once you dig a little bit deeper into this into the kind of effects that this intensive farming practices have on quality of food, and that and also the environmental impacts of such farming practices, then our development of biochar and compost started to make even more sense. Because in these intensive farming practices, the only rule is to produce more yield per hectare. And what we are already seeing now, and what is also now starting to be talked about much more, is that the food that is produced in these with these intensive farming practices is nutriently really very poor. So we can have, for example, a plate of spinach that now has less than 1/10 of the iron that, for example, traditionally homegrown spinach had, let's say, 20 years ago. So we are actually eating the same amount of food, but getting a lot less nutrients into our body. And this becomes, over time, as I will also explain, becomes it brings certain aspects of issues with this. And this is now already quite talked about, in a sense that mostly this civilized world, we people are overfed because we eat larger quantities, we have very high availability of food, but we're still, from the nutrient point of view, still undernourished. And this is exactly kind of what is happening with these intensive farming practices. And what me as a microbiologist, and also with what we're doing in these sustainable, trying to implement these sustainable practices, is that we have to be aware that the soil is much more than just something where we grow food, that the soil is actually very much alive. If we would to take a small spoon of soil from the forest, where now these are the most untouched soils, there would be more living organisms in one spoon of soil than all humans on our planet. So there is a very high diversity of protozoa, of bacteria, of fungi. Under our foot, if we step on a very healthy soil, there would be like 10 kilometers of fungal hyphae. So there is a lot of life happening. And if we want to grow healthy food, the most important principle to adopt is that we have to nurture this life in the soil. Because if the diversity of life in the soil is reduced, the quality of food is reduced. Quality of everything that grows on this soil is reduced. So, and if we want to support or increase the life of this soil, of course, we need food for these microbes and this life, and we need to increase diversity. And so if we look at this diagram, I always find it very fascinating that if whatever we see on the surface is a very small segment of what everything needs to happen underneath the soil, all the interaction, all the symbiosis, all the nutrient exchange, all the communication that has to happen underneath the soil so that we grow a tomato. And this is the part where we're mostly now in these intensive farming practices completely ignoring, and we're only concerned with this upper part. And if we want to sustainably grow food, first thing is that we need to start being aware that this underneath the soil is the key to whatever is going to be on the upper part for us to see, to eat, to grow, to nurture, that we have to start with this part. First and foremost is, of course, because plants form very intensive symbiotic relationships in their roots. They form symbiotic relationships with bacteria, with fungi, with certain types of algae. And without this, basically, the plant has very little, very much smaller nutrient pool, much smaller place from where they can take water or everything that basically they need. These symbiotic relationships are very crucial for the plants, not only survival, but also how much they can grow and how much nutrients they can absorb. So if we want to look at a circular model of our own well-being, from what kind of air we breathe, what kind of water we drink, what kind of soil we grow our food in, it's always we have to start with the soil. If we don't have a healthy soil, there is very little that can come, very little positive effects can come to us as humans from a nutriently depleted and poor soil. So this is where we have to start. And this was also kind of the basics of why we started to think that we need to do more than just compost, that we need to start thinking about the soil from the point of view that this is like a microbial diversity, that we need to store carbon, increase microbial diversity, and that we have to give it some kind of coral reefs or kind of haven where these nutrients and microbes can find their habitat and stay there, even if, for example, droughts happen, even if the temperatures rise. We have seen very clearly all around the globe all of these extreme weather situations, what they do for not only for humans and civilizations and everything that kind of comes with this, but also what it does for growing food, what it does to the soil itself and for crops that we're growing. So if we embed something into the soil that can function as this kind of a buffer system, that can function as coral reef where all of this finds their space and their habitat, maybe we can do we can kind of tackle several aspects of this soil health and fertility. So once we had these mixtures prepared, we did many experiments. We had experiments in pots, we had experiments in these garden beds, we had experiments in larger areas. We experimented with very different crops, from barley and wheat to lettuces and tomatoes and all kinds of different plant varieties. And the experiments always showed a very similar picture. When we added compost in the combination with biochar, not only was the yield bigger, but the plants were always healthier. They were much more robust. They were much more, let's say, they had the capability to fight off pests. When in summer the temperatures went very high and there was drought, they were much more resilient to these kind of abiotic factors of the climate. So we saw in all cases that the addition of biochar, activated biochar, gave the plants a huge advantage over the ones that didn't have this. And if we look at historically what was happening on our planet, it was that there were a lot of fires, and kind of biochar was normally produced. And so plants kind of have a coexistence and kind of co-evolution with this biochar in the soil. And also humans realized this early farming of the humans usually looked like that they burned down a part of the forest, and then this is where they grew food. So this is kind of a practice that the humans first adopted from looking at what's happening in nature. And plants kind of, they know how to coexist very well with this. And when we looked at the roots of the plants, we always saw that the plants integrated their roots into these biochar pieces. So it was a really intense symbiosis with this. Of course, because we were doing experiments, we also wanted to see how much of this biochar is enough, and if there is such a thing as too much biochar. And a very interesting thing happened that we were not expecting is when we added, so if we added up to 20% of biochar in this top 10 centimeter layer of the soil, the plants were very happy. Once you kind of gave them like 5%, there was a visible difference in how much the plants grew and also how much water they needed. And then up to 20%, they were happy. But if we added over 20%, they weren't unhappy, but their growth stood still. And this was very fascinating. And of course, as researchers, we always do, we go back to the literature and look if someone else saw similar effects, what is happening. This topic of biochar is fairly well researched in the world. And we saw that other researchers found very similar findings. And it turns out that because plants have such a long evolutional history with fires, with biochar, they kind of have I don't know how this wasn't it's kind of a mechanism in the plant that if the biochar is very abundant in the soil, this means that there was a recent fire, and they kind of stand still. They kind of wait for better environmental conditions to start intensive growth. And we and also other research groups found the same thing. So we can't add too much of biochar into the soil, because the plants are just gonna think it was a fire and kind of go like, oh, yeah, we will just wait it out. So the general recommendation now is that we kind of add up to a liter of activated biochar per square meter, and kind of work it into the top 10 to 15 centimeters of the soil. And this is how it has proven best in all of our experiments, either in with all of these different crops. For example, what in Slovenia mostly is grown in summer and in fall are tomatoes. And tomatoes, for example, were extremely happy with biochar. For example, if we look at this first section, this was just a typical substrate you buy in a shop and grow from seeds. And this one was where we added activated biochar. You can see that it's almost twice as tall. And as I mentioned, one of these also crucial advantages of biochar is also that you need to water these crops much less, because water stays bound in this biochar. So it's also much less maintenance. We've also seen that the soil becomes much more loose. It's much easier to work with this soil. It needs much less tilling and much less physical work. And from an ecological point of view, the hugest advantage is this, that we're actually, so if we think, so biochar is like 95% carbon. So once we add biochar as a soil improver, we are actually returning carbon into the soil. And biochar is very stable. It has these bonds between the carbon atoms are very strong. So between 300 to 500 years, this carbon remains in the soil. It does not get released into the air via CO2 or similar gases. So we actually bind carbon into the soil, and we actually increase this this capacity of the soil to function as a sink of carbon. So not only are we improving soil structure, we are increasing water retention, we are increasing the yield, we are giving the soil the chance to bind or kind of give home for these beneficial microbes. But there is also a humongous advantage in regards to climate, in regards to this circular economy or circular principles, where we're trying to kind of function as counterweight for these emissions of carbon, so that we bind carbon into the soil. And biochar is also very alkaline. So it when we add it into the soil, it increases the pH value. So this is one of the things that we have to be kind of a little bit mindful of, because it's not directly appropriate for all soil types. For example, our Pomurje region has very acidic soils, so here it's perfect. But for example, the regions in Slovenia that are closer to the coast have a more alkaline soil, so there we have to prepare the biochar a little bit differently, maybe activate it via different strains of microbes that have lower pH values and kind of reduce pH. But this can all be kind of tailored for specific soils. Because we are functioning in Pomurje region, we focused on this, that the fact that biochar by itself has a higher pH value is beneficial, because most of our soils are acidic, and farmers anyhow always add lime or similar things, so that they're raising pH towards the neutral. So for our region, this is also a very important factor of what biochar can bring to the soils. So we are actually, via this, we are kind of trying to come into this cycle of carbon, so that we produce carbon that is very stable, and we put it into the soil, where then it is stable and stays stable for centuries, and we can actually produce and increase this sinking of carbon into the soil. One of the important things that this also brings is another very important aspect. I briefly mentioned this in the beginning when I was explaining that this intensive agricultural practices are producing food that is nutriently fairly poor, or has very little nutrients per kilo, let's say. Because in intensive agricultural practices, they usually use mineral fertilizers, where they add phosphorus, nitrogens, and kalium. And as a consequence, of course, the plants that are growing mostly have only these three elements available. But as we are learning now more and more, plants and also humans, we don't need only these basic elements, or let's say these macronutrients. We also need basically the entire periodic table of elements for healthy plants and also for healthy humans. A lot of them are needed in the human and animal plant cells as trace minerals, so we need very, very little of them. But if they are not available for a very long time, there's very specific conditions can emerge. Sometime, let's say maybe like 20-30 years ago, scientists showed a very clear link between too little vitamins and diseases that happen due to that. Now in medicine and also in other like nutritional science, it's becoming very clear that there is also a very strong connection between minerals and health, and that certain minerals that are needed in very, very low amounts, but if they're missing over a long period of time, they cause very specific conditions. If I say only one example, for example, the element boron, if it is missing, it is missing in 95% of patients that have rheumatoid arthritis. And if they start adding this boron, then the inflammations in the joints are drastically reduced. And this element is naturally present in soils, but because of these more and more depleted soils, the plants don't have it, so our food doesn't have it, so essentially humans don't have it. Now, there is also the reason why these connections are coming maybe now in the last years is because we can be the minerals, we have fair amounts of minerals in our bones, in our teeth, and if the body is not getting them via food, we can take them from these reserves. But also we for certain symptoms to appear due to mineral or like element deficiency, it can sometimes take 10 or 20 years. So this connection is not very obvious. One has to look very, very deep and have a very consistently looking at what someone is eating and drinking, and then what happens and which elements are happening where. For example, selenium, we already know now that is very vital for thyroid function. Chromium is very crucial for how our body metabolizes sugars and fats. Usually they are like very crucial elements in enzymes. So if, for example, we don't have enough selenium, certain enzymes will not function. And the consequences of this sometimes become evident 10, 20 years later. So this is the reason why we're now kind of starting to see these connections. And many of these elements are very necessary and crucial in small quantities. But if we have a lot of them, which now, for example, also are cases with these different pollutions that are in our environment, and as a consequence, of course, in our bodies, when we have too much of, for example, I don't know, iron, it becomes toxic. If we have too much of chromium, it becomes toxic. No? So, but if we don't have it at all in our food and in our body, we also, can experience different symptoms. And this is why it's so crucial that our food that we are growing has all of these minerals and trace elements available, because if the plants absorb it from the soil, then we will of course eat it via the plants and have these elements in our bodies. So, and this is what also microbes do very efficiently. So if we have a very good microbial diversity in the soil, there will be many more elements in such forms that the plants can absorb them. We will have much more diverse array of these minerals and microelements, because microbes are very good degraders, so they will take different organic particles in the soil and degrade and make available everything that the plant needs. So this is one important aspect of why, if we add biochar into the soil, means that we bring a lot of beneficial microbes. There is a huge microbial diversity, which means much more elements, much more minerals, trace minerals available for the plants. And of course, as everything comes back to humans, when we eat it, we bring the majority of this periodic table into our bodies. So we came pretty far with this idea of biochar. We did all of our due diligence. We did the lab experiments, we did the field experiments. And based on all of this, what we gathered, we came together and produced a product. We called it activated biochar. This product also received the Slovenian Innovation Forum Award for innovative products already quite some years ago. This product was also listed in the catalog of good practices for reducing CO2 emissions. And we did all the registrations and everything, and we put it out into the market, where we kind of realized that people have a very limited knowledge about this. That people do not really know the difference between biochar and compost. Many of them don't even fully understand the benefits of compost versus mineral fertilizers. And as consumers, they look at the price, and biochar was more expensive than compost for, let's say, per liter of the other one. And the sales were really not happening. We invested a lot of effort and time into raising awareness about it. We went to many fairs that had to do with farming, and we gave a lot of lectures. We organized the symposiums and everything, but kind of this there was a small population of like biodynamical farmers and also owners of home gardens and like balcony gardens in the cities that were interested, and very fastly saw that this means much less work for them, much less watering, much less it takes much less tilling for the soil to become like nice and ready for planting of something. But mostly the product did not take off in terms of sales and marketing. So I think after like 5-6 years of kind of struggling on the market, we took it off the market. We are now thinking of maybe kind of restarting this practice to see if the mentality or maybe the ideas have started yeah, maybe the general climate has changed a little bit and people are more aware of the need for yeah, to just take care of the soil as a whole, to not anymore be concerned only with tomatoes and lettuces, but also be mindful of what we do with the soil. So it was for me very fascinating that there are many research groups around the world that are researching this biochar, and there is a very there's a very good researcher in Germany that did a lot, especially in regards to climate change and biochar and this sequestration of carbon into the soil. And his research group calculated that if only 10% of the agricultural soils on the planet would incorporate biochar into the soil, our civilization would not only become carbon neutral, it would be we would become carbon negative. If only 10% of agricultural lands would use biochar. So I find this very fascinating, and it's something that basically anyone can do. Even if you don't have a garden, most Slovenians will have plants in pots at home. You can just add a handful of biochar into the pot and know that you have stored some carbon into the soil for the next 300 years. And even if you toss this away, it will still store carbon in the soil. And since a lot of people are actually having at least balcony plants or their own gardens, I think this has a humongous potential, and it seems it doesn't take humongous amounts of technology. It doesn't take that we kind of change everything in our lives to become environmentally friendly. We can just take a handful of biochar and put it in our plants, put it in our gardens, and make at least a small contribution to what we as a civilization are doing to our planet. So I would conclude with this, the first part of my presentation, and maybe open for questions. And then after the break, I will continue with the other part.
Thank you, Tanya. I think it was very informative and very revealing and very well explained, also for us amateurs.
Thank you. I'm hoping that everyone would, if it was sold, run and buy a little bit of biochar and just toss it somewhere.
Yeah, maybe your years behind before the time, or how should I put it? You were
Yes, ahead of time. Yeah.
ahead of time. I wanted to say, of course.
Yes. Yes, it did seem most of the discussions I had with potential buyers was, so how's this any different from compost? And I can buy compost and like 600 kilos for 20 euros, and here I have to pay 5 euros for these 2 liters. So how does this make sense? And I'm like, but you put this once in your lifetime and it stays for your grandchildren. And but it didn't really it didn't stay in the mind. It was still only kilos and euros, and we couldn't get much past that. Yeah, maybe a little bit ahead of time, but yeah, the environmental and climate changes that we are all seeing, and I don't think there's a country that has not been touched by this or affected by this. Maybe has caused enough changes in our way of thinking that maybe we will be like people, like consumers, more open to things that have long-term effect. No? I thought that one of the crucial things will be, because people are by nature very lazy, that if you tell them that they only need to water half as much as they did before, that this will be the winner. But it turned out that people really like this idea that they always have to go, that it gives them something to do. So this was also not a winner for this one. So I will present the second example of how in this waste management strategies or industry we employ circular economy practices. And this example is a little bit less well researched, because it's quite a difficult topic to research, and we have not come as far as I have shown in the previous example. So this is a case where out of certain specific types of plastic and waste, solid or refuse derived fuel is produced. And our idea is to use this fuel to convert it back to something that is called plastic crude oil, that can be used as a substitute for fossil fuels, or at least part of fossil fuels. So I will talk a little bit about what these refuse and solid derived fuels are. Where do they come from? How are they composed? What are their characteristics in a lab, and via what processes can we produce something from them that actually fits into the circular economy model, and what, of course, we are doing currently with it, and what are the challenges ahead. As we all know, we are mostly in Slovenia and also generally in Europe quite well already educated with waste separation. And then this waste is collected, of course, brought to different centers where this waste is then via different processes managed. And a lot of focus has been given to recycling. But even when we use the best recycling and all the recycling possibilities, there is still a lot of packaging materials, a lot of textile, a lot of paper products that are not appropriate for recycling. And this, out of this section of packaging, textiles that cannot go to recycling, is kind of left over and ends up in this refuse derived fuel. We call it RDF for short and for simple. And then usually this RDF is used as a fuel or co-fuel for these huge incineration facilities, or for production of concrete, or for production of electricity and warmth. And this is like almost practically inevitable part of waste management. There are always materials that are not appropriate for recycling, and those materials also need to go somewhere. Europe as whole and also Slovenia adopted zero waste principles, which means that we are very focused on reducing or coming close to zero to how much waste is ends up in landfills. also incineration is not something that would be preferred. So, but still, no matter how, there is still a lot of waste that cannot be recycled, and this is where RDF comes from. And this is a video from CEROP for in Center Management for Waste in Puținți, where and how this fuel actually looks like in practice. So everything that is not taken from these transporting convoys is then goes automatically to a shredder and falls down like this. This sound you hear are naturally very heavy shredding machines. And basically, the way I look at it, fuel is falling from the sky. And this is fuel if we would look at only the characteristic of a fuel, it's a very, very good fuel. It has almost triple the calorific value of wood. So it gives off a lot of energy when it is incinerated. When we look at the composition, it is mostly composed of different varieties of plastic. As I mentioned, there are many different varieties of plastics, and not all of them have the qualities that would enable them to go into effective recycling. So many of them are have like single use, although this is being strongly reduced, but still there are a lot of such plastic materials. There is also some wood, some paper that has, for example, been wet and cannot go to paper recycling. There's also a lot of textiles. Also textiles that are mostly made of artificial fibers, not of natural fibers. And this is about how this fuel that is falling from the sky these are actually the most of the ingredients. As I mentioned, the calorific value, so how much energy, so how many calories per gram does this fuel emit when it is burned, is quite high. The fuel that is being produced in CEROP has even higher, mostly calorific value. Particle size are usually between 5 and 3 centimeters, and we make sure that the moisture ratio is very low. So for incineration, it has to be below 18%. So we usually this material goes to a process of drying, and then it is stored and waits for transport. So if we look at if this fuel goes into incineration, these are kind of the necessary parameters. Such fuel has to either go in a cement kiln, either go into incineration as a sole fuel, or together with some other fuels. Mostly we look at the calorific value, we look at the content of chlorine, the moisture, and how much ash remains after the incineration. And our fuel mostly has very high calorific values, so between 26 and 30,000 kilojoules per kilogram. Chlorine content varies very much because it depends on if these batches have a lot of PVC, which is polyvinyl chloride, then it has more chlorine. If it's other types of plastic, then less. Moisture is usually can be regulated. At CEROP, there are specific sites where this fuel is then being dried, and the ash content. So these fuels are also kind of graded in different categories depending on their qualities. CEROP has a small lab where all of these can be tested. We can test for the calorific value, for the chlorine content, for the moisture content, ash content. So we can kind of have an internal control of what kind of fuel we are producing. And mostly we are in this either first or second class. The calorific value is pretty high. We have many times issues with the chlorine content because polyvinyl chloride is also a type of plastic that is not that does not have a very closed loop when it comes to recycling. So a lot of the plasticking and packaging materials that have polyvinyl chloride will end up in this fuel because they don't have any other ways of being either reused or repurposed or recycled. So this chlorine content is sometimes problematic, but mostly we produce this RDF fuel that is of on the higher end of quality. So at the center, this is usually what happens. We collect waste that come into the center. Here it is. It goes through different processes of dealing with this waste, and this refuse-derived fuel is one of the products that come off. Then it's being dried, and usually it is then transported to some of these end users, as I mentioned before. So these end users are either in the production of concrete, so these cement kilns or lime plants. Then there are also some incinerations, like industrial furnaces, furnaces that are meant as a combined production of heat and power. There are also some gasification plants. And in Slovenia, basically, there's only one incineration plant that is run on this RDF. That one is located in Celje. But in Celje, they only accept, they're only solving their own regional problems. So they have an incineration plant for waste that is derived from the Celje region. Well, as you can imagine, mostly people do not want to have incineration plants as their neighbors. So wherever there was an idea to position such a plant, there was a lot of, let's say, backfiring from the communities. And we don't have any other functioning incineration plants in Slovenia. So the solution is that Slovenia is exporting all of these RDF fuels. Mostly we are exporting to Slovenia, Hungary, sometimes Slovakia. And this has been fairly well functioning for the past maybe 5, 6, 7 years. This functioning, I mean primarily that Austria and Hungary were accepting these fuels. There was always a lot of debate about what were the prices of these fuels, because such centers have to pay for Austria to take this fuel, or Hungary, and the prices were every year higher. And also many times when they wanted to drive the prices up, they just didn't accept for a few months, so you didn't have anywhere to store and essentially accepted the price sooner or later. Now in the last year there has been a huge shift in this, where Austria, Hungary, and Slovakia did not accept these fuels anymore, which caused a lot of problems for majority of centers in Slovenia. where this high energy fuel was being stored in huge quantities. So we're talking about several thousand tons of this fuel. And if you remember that I mentioned that this is very dry material and very high calorific value, this poses humongous threat for fire breakouts. And most centers in Slovenia already had such instances where this fuel did catch fire because of internal. So it's a high calorific dry material that is stored in huge quantities. Usually inside of such a pile, there will be, the temperature starts to rise. And these are not usual fires. You don't even see anything for a long time with the naked eye until this core is kind of overheating. So it's a very, it becomes a very big issue to manage high quantities of such fuel in these centers. But as I mentioned, Slovenia kind of didn't reach agreements with these countries. So countries like Hungary, Slovakia, Austria, Germany, Netherlands stopped accepting these fuels. And since we don't have an inside solution within Slovenia, this just becomes a burden that is not properly addressed. So other than that it goes into an, so if we look at, until now I said that this kind of this process flowed fairly smoothly, but also definitely not in a circular economy model, because such centers produce high quality fuel that has very high calorific value, essentially then transports it to another country with very high transportational cost, with very high carbon footprint, and then this is essentially burned. It does produce some electricity and some heat, but this is also not really in circular economy model of thinking. So we were, for some years already, we are intensely researching what else can be done with this. What would be the possibilities to somehow not burn it, but somehow make a material conversion out of it to produce something that will be usable, something that will enter back into the circle of materials or elements. And one of the things that we have seen that was being done elsewhere in the world is gasification of this refuse-derived fuel. Via gasification, there is a production of methane and CO2 and H2. And these, methane and H2 are very energy potent gases that can then be used either for transportation or for production of electricity via, for example, cogenerations and similarly. So actually you kind of extract raw energy or pure energy from this refuse-derived fuel. The downside of this, that this demands really very technologically very advanced equipment, also very expensive, very high investments, and then you get products that are highly volatile and also have high explosive potential. So this part also demands very careful handling. Transportation of these gases is problematic or very expensive and very dangerous. So we kept looking at what else can we do. And one of the things that from my perspective and also many other researchers that holds a lot of potential is pyrolysis. This is a word I already mentioned in my previous example. Pyrolysis is also a possibility to produce biochar. But pyrolysis in its definition is only means that there is that you have a reactor that operates at high temperatures and doesn't have any oxygen in it. So there is no burning, there is no emissions like in incineration. So these are always closed loops. So any gases that are produced are returned back into the reactor. So there is no like emissions into the air. And what happens during this pyrolysis if we put RDF inside is that these polymers get degraded, and there are many ways that we can kind of lead this process of pyrolysis. We can change the pressure, we can change the temperature, and we can get different products out of it. For our material, we find that the best, there's a question.
Yes, thank you. Do you have a station in Slovenia for pyrolysis?
No, not a single one.
Thank you.
We are hoping that will change, but currently there is not a single one. There was a huge legislational hurdle because pyrolysis was placed in the same frame as incineration in Slovenia. So no matter what you did, even if it wasn't, of course, natural, like classical incineration, you had to get the same, you fell into the same legal frame. This is also now changing in this new proposition of the environmental law. There is now a change where pyrolysis could in fact be implemented for waste management. So maybe now this will open doors for the first ones to appear.
We have a company, he would like to found a new company in Austria, in Carinthia, but we talked about since 3 or 4 years. It's a long way, but
yeah.
I don't know the reasons. But we have a Swiss company partner, and he will build this in Carinthia with the circular economy, with plants and so on. It's very interesting. Then that was my question.
Yeah, well, we are very open to discussions for it, because once these legislational frames enable this, I think all of centers for waste management in Slovenia will be looking at something like this, because currently there is just no viable solution. No, so this I think will have a huge leap in Slovenia once this is kind of, in terms of regulation, has this new frame confirmed.
Thank you.
Yeah, so for the material, for this material RDF, we find that the best way to lead the process is so that we get as much as pyrolytic oil as possible. So the product of pyrolysis, we are 3 products. One is gas, one is the liquid fraction, and one is the solid fraction that remains. So depending on what kind of temperature is chosen for specific materials and what kind of pressure is chosen, we can either, if we have very high heat and high pressure, we produce more gas. If we have a little bit lower temperatures and pressure, we produce more of the liquid phase. And we find that with these plastic materials, with this refuse-derived fuel, the best solution would not be gas, but the best solution, at least for our case, would be production of pyrolytic oil. There is always some solid fraction remaining. For that, we still have to figure out exactly what are its characteristics and what can be done with it. We presume that what comes out could be added as in production of asphalt, but we have to see about that. But I'm sure we can find also a circular model of what to do with this solid fraction. But for now, we're working intensely on this, that we would produce pyrolytic oil out of it. Via different, we need to have a temperature, we need to have pressure. So we're kind of a little bit simulating the conditions of how fossil fuels are made. You know, between these tectonic layers, there is also higher temperature, higher pressure. This is how fossil fuels are made. So we're kind of a little bit simulating that as well. So raising the temperature, adding pressure, and this is how these polymers from plastic can be liquefied again. And this is what we are trying to do, so that through this waste plastic, we would produce pyrolysis oil. There are already plants, even in Europe, that are already doing that, where, for example, the input is our old tires, or also waste plastic. Also other lands, other continents are even more advanced with this pyrolysis as being a part of waste management. It's not the answer to everything, naturally, but it can be an important part of how we are recirculating something that would otherwise just be incinerated. If we use RDF and put it through a pyrolytic process, we're mostly focusing on the liquid fraction, where we can then further refine this and get different either biofuels for typical diesel engines, or even advanced fuels, and we can get phenols extracted from it. Depending on how far we want to take this refining process, we can get different fractions out of it. What we are mostly focusing on is that we would get to this part. So the idea is kind of to get pyrolytic oil. We already now know that there are companies in Europe that are buying pyrolytic oil, already crude pyrolytic oil, but there is fairly little refinement necessary that this biofuel can be returned into the circle of fuels and actually re-enter into gas stations so that it can be used in diesel motors. So if we look at where plastic is coming from initially, so we start with fossil fuels and crude oils, and also through a lot of refinery we get naphtha from which plastic is produced, and now we're basically circling back to crude oil, but not made from fossil fuels, but crude oil made from plastic. And this is why this has an abbreviation PCO, plastic crude oil. And this is what we are trying to do. Usually what comes out are kind of like these dark colored oils that then can be further cleaned. This, of course, what are the exact contents of this pyrolytic oil also strongly depends on what we use as input. As I mentioned, in this RDF, we mostly have a mixture of many different types of plastic, which is not ideal. There's been already a lot of research done on pyrolysis, but mostly they decide to use just one type of plastic, and then you can optimize your temperatures and pressures so that you really get as much and the best possible quality of this pyrolytic oil. But when you have mixtures of materials like we have, this is why we need to do a little bit of research specifically on our materials to see if, for example, a lot of time a contaminant of these pyrolytic oils are sulfurs, and they are damaging for the diesel motors. So, for example, this usually needs to be either removed or sent through certain colons to be cleansed, or certain distillation processes, so that then we get a fuel that can be reused in diesel motors. So we kind of spare some of the fossil fuels, and we can, through the plastic that is already produced, we can circle it back into the as fuel back into the diesel motors. So this refinery, usually these cleaning process steps, or distillation or refinement processes, are usually very well clearly visible to the naked eye. Usually we start with a dark color and we remove different contaminants or different compounds, and we become we get to a fairly more clear color already. So it depends, but from what we've done, our own kind of analysis of the current situations, there are already companies who buy pyrolytic oil only based on how much of the calorific value this pyrolytic oil has, because they already have refineries and different distillation steps that then they do. So from a point of view of such a waste center, this seems already like a huge problem solved. So you can, from something that takes up humongous amounts of volume, because this is a very kind of a fluffy material, you can liquefy it and sell it, because now we have to pay quite high taxes so that we are allowed to transport waste to other countries. Then we have to pay huge amounts of transport, and we have to pay for other countries to take this fuel. And now if we would come to a place where we have liquefied this and we are able to sell it, this is already like a quantum leap from where we are currently. I'm not saying that this is a perfect solution for everything, but if we are thinking about the circular model, this is much, much closer to it than where we are standing at this point. So this is what this is how this RDF looks up close. So you see, you can have particles of different size. For pyrolysis, it's better to have particles of smaller size so that the temperature gets faster to each particle. And you can see that there's very different materials in here, from cardboard, paper, plastic, textiles, different types of foils. Everything that doesn't go into the recycling, it doesn't have a kind of a loop of its own, gets into this fuel. And what we're trying to do is actually produce liquid plastic crude oil from it, so that it would kind of enter back into this material circularity and wouldn't just be up in the air we go. Currently, we are at the stage of a lab scale. We are doing first experiments with the like a lab scale pyrolysis machine that was designed specially for our material. So this was done in agreement with our ministry to have only lab quantities. There is a pyrolysis reactor where we will have a lot of possibilities to take samples of the gases that are being produced and of the liquids that are being produced from different temperatures, from different pressures. And this is aimed that we figure out, so we have a very specific composition of this fuel that we produce. What is the best temperature? What are the best conditions for pyrolysis of our specific materials? We annually produce around 15,000 tons of this material. So like in a scale of the whole Europe, it's not a lot, but for a small center, for one region in Slovenia, these quantities are humongous. especially if you have to store them somewhere. This is a storaging capacity of hectares, not square meters. Some tests have already been done on this lab machine, and we will continue this. We have also established cooperation with an Austrian consortium, where we will exchange knowledge. From what we know, we've also been granted an Interreg Slovenia-Austria that covers this topic now, and we will be able to kind of exchange where Austria already is and where we can go and what they have learned from their experiences so far. So in a way, this is kind of not perhaps the best the cleanest way, because it still is waste and it still is kind of high temperatures. So if you imagine that this pyrolysis reactor has to sustain temperatures around 600 degrees, it does demand input of energy, especially in the beginning. Then we can kind of circle back some of the energy-rich gases and keep the temperature high in this way. But for when we start the process, we of course have to give it quite a lot of energy, so it's not as innocent as we would want. Of course, we are also aware that it takes it has its shortcomings, this idea or this technology, but we are taking this development step by step. But as I mentioned, most countries in Europe do have high production of this derived fuels. They do use it mostly purely as incineration, and if we can turn a part of this fuel back into, let's say, simulate nature and liquefy, so we can replace some of the fossil fuel, I think this is quite a big step forward. We are also thinking that we could employ this very locally. Such centers have a lot of demand for fossil fuels in terms of we have machines that, and also transport trucks. So if we would get to the point where we could use some of these fuels ourselves, or at least somewhere locally, this would also be a huge step forward in reducing carbon emissions, in reducing carbon footprints. So this is what the next step in this circular of trying to implement as much of circularity as possible in this field of waste management. I know it's not the most, usually we talk about circularity first when it comes to energy and materials and so forth. We are usually the last stage in this process, but we do have a research team, and we are trying to think a little bit ahead of time and try to find solutions that are as close as possible to these circular principles. We are aware that we as civilization are making humongous effects on our ecosystems, on everything that we touch. And waste is usually like this, where we are the dirtiest. So if we can change some things that reduce the impact of our activities towards the planet Earth, we are strongly engaged in that way of thinking and in trying to find things that are already working perhaps in other countries, and implement it, do our research, do our due diligence, and get into practice with things that will make sense also on the long term. So also in waste, we have already stepped far away from this linear way of thinking. And for a while, for maybe last 10 years, it was in waste, we were mostly thinking about recycling. What else can we recycle? What else can be kind of put back? And then we come to a place where we realize that if we do everything recycling that is possible, we still have a lot of leftovers, so to speak. Yeah? We still have a lot of materials that don't have anywhere to go. And now if we can find a way to kind of circle back with the material, and as I said, maybe even replace some of these fossil fuels that we know that carry a lot of problematic issues from every step of fossil fuels. If maybe this plastic crude oil can partially come in place of these fossil fuels, I think that a lot of the criteria for circular modalities are met, and I think we can reduce some of the effects and harm that we are doing as a civilization for our planet. So this would be it from my side for this second